Hi everybody, my name is Hazhar Rahmani. I will be presenting the paper Planning to Chronicle by me along with two co-authors Dylan Shell and Jason Oken from University of South Carolina and Texas A&M University. Consider an autonomous robot equipped with a camera. Its job is to record a video consisting of a sequence of events matching some specification provided by a user. The world in which it operates is stochastic. So while the robot knows what kind of events may occur, it doesn't know with certainty when or where an event will occur. Because it takes time to move and set up in order to capture footage, the robot is faced with the problem of anticipating the future. Specifically, if it predicts that some event will likely occur, it must assess whether it would be helpful to try record that event for the user's intended video. If so, it attempts such a capture. We are interested in how the robot should act in order to record a suitable video in the shortest amount of time. As a concrete example, consider this depiction of a wedding reception. In this specific example, the robot is tasked to record a very simple event sequence in which first Alice and Bob are dancing, and then either Chris is drinking coffee or Alice is smoking. The robot first decides to capture Alice and Bob dancing. That event occurs, and because the robot's prediction was correct, it succeeds in recording it. Next, it decides to record Chris drinking coffee, but it fails to capture that event because that event does not occur. Next, the robot decides to record event Alice smoking in the next time step. That event does occur, and the robot records it. This completes the robot's recording as it has a video meeting the given specification. The contributions of this paper are an algorithm for the problem of computing a policy that minimizes the expected number of steps to record a desired story in an unpredictable environment, a theoretical result on representation invariance of expected time, several language mutators, and two case studies. Our problem involving story capture can be viewed as the inverse of the topic of earlier work in validation of stories. That work studies the problem of determining whether a given story is consistent with a sequence of events captured by a network of sensors in the environment or not. Two other and also closely related problems are the video summarization problem and the vacation snapshot problem. The main task in those two problems is to make a good summary of data that is already available. But the essence of our problem is to decide which information to collect in the first place. We treat each event as a letter from a finite alphabet E, and accordingly we treat a video or a story as a finite word in E star. We model the occurrence of events using an event model coupled with an observation model, which together form a hidden Markov model. This figure shows an event model with its observation model for the joint behavior of Alice and Bob, who participate in a wedding reception, and each one of them at each time step could be either in state of dancing or in state of smoking. Each state is assigned by the labeling function G a set of events. For example, state S1 is assigned events SA, which denotes Alice smoking, and event DB, which denotes Bob dancing. In this example, there are two observations, X and Y. X represents nothing, and Y represents the observation of detecting smoking. Each state is attached a distribution over the set of observations. We specify the story or the video using a deterministic finite automaton. The observation model described in the previous slide is quite general, but the paper also devotes some space to detailed treatment of two special external models. Case 1, the fully observable model, in which the current state of the event model is always known to the robot, and case 2, in which no state information is provided to the robot. During an execution of the event model, the system passes through an infinite sequence of states. At each time step, when the system enters a state, all events assigned to that state happens simultaneously, and an observation is produced based on the emission probability function. The robot maintains for each time step a belief state over the state space of the event model, the current state of the DFA, and the sequence of events it has captured until that time step. At each time step, the robot chooses one event to capture in the next time step. If the robot chose an event to capture in the next time step, then it is committed to capture only that event in the next time step. The robot choosing of the event is governed by a policy pi that depends on the current belief state and the current state of the DFA. If that event happens in the next time step, then the robot records it and it updates the current state of the DFA. Otherwise, it records nothing and the current state of the DFA is not changed. To illustrate, we run an example. The DFA specifies a story that shows a person first smoking and then dancing. Initially, the DFA is in state Q0 and the event model is in state S0. The initial belief state is a vector that has outcome only for S0. The robot chooses event Ali smoking to record in the next time step. In the next time step, the event model transitions to state S2. Because the chosen event Ali smoking does not happen at S2, the robot records nothing and accordingly the DFA does not progress. The robot makes observation Y and based on that it updates the current belief state, which shows that with probability 1 the system is in state S2. Note that the robot knows that S1 cannot be the current state because the predicted event SA always happens at that state. Then the robot chooses event Bob smoking to record in the next time step. In step 2, the event model transitions to S4, and because the predicted event does happen in that state, the robot records SB and updates the current state of the DFA to Q2. The robot again observes Y and updates its belief about the current state of the event model, which shows that with probability 0.44 the event model is in state S2 and with probability 0.56 the event model is in state S4. It then chooses event Bob dancing to record in the next time step. In steps 3 and 4, the robot does not record anything because the guessed event does not happen. Finally, in time step 5, the robot captures its predicted event and the DFA reaches to its accepting state. Accordingly, the robot stops guessing and recording events. The main problem we study is called the recording time minimization problem, or RTM problem for short. The inputs of this problem are an event set E, an event model M with its observation model B, and a DFA D. The output is a policy that minimizes the expected number of steps to record a desired story. As we pointed out, we consider two special cases of observation models, one that makes the event model to be fully observable and one that provides no useful observations. Both of these models lead to special variants of the recording time minimization problem. The expected number of steps to record a desired story under an optimal policy for RTM is always bounded between the expected number of steps for RTM with fully observable model and the expected number of steps for RTM with fully hidden model. In fact, we predict that as state observability of the event model decreases, the expected number of steps to record a desired story increases. Our algorithm to solve RTM and the two variants of it first makes a PAM-DP as a product automaton of the inputs to the problem, and then computes a policy that minimizes the expected number of steps to reach a goal belief state of this PAM-DP. A belief state for the PAM-DP is a distribution that gives for each state the probability of being in that state. A goal belief state has outcomes only for the goal states. In this example, only B2 and B3 are goal belief states. Each state of the PAM-DP is a tuple SQ that indicates the situation where the event model is in state S and the DFA is in state Q. The set of all events constitutes the action set of the PAM-DP. The PAM-DP has a set of goal states, each one of which indicates a situation where the robot has successfully recorded a desired story. Each transition of the PAM-DP corresponds to a situation where the robot chooses an event E to observe and the event model makes a transition from a state S to a state S'. If E appears at state S', then the robot records E and then makes a transition in the DFA. Otherwise, it records nothing and the DFA remains in state Q. All the goal states of the PAM-DP become absorbing states. At each time step, the robot makes two observations. One, whether its prediction of occurring an event was correct or not. Second, the observation Y omitted from the event model. Accordingly, each observation of the PAM-DP is a tuple consisting of a Boolean value and a sensed observation from the event model. There is also a special observation, falsum, which is observed only when a desired story has just recorded. Rules A and C are for the cases where the prediction of is happening was correct, while rules B and D are for the cases where the prediction of is happening was incorrect. Rule E is for the case where the robot has successfully made a desired story. Computing exact solutions to PAM-DP is generally intractable, but algorithms for computing approximate solutions exist. We use APPL Online Toolkit, which implements one of the fastest known PAM-DP solvers called the Spot. We solve the RTM with fully observable model using the goal MDP underlying the goal PAM-DP rather than the goal PAM-DP itself. MDPs are tractable to solve. We now present a theoretical result. Consider that the event chosen by an optimal policy depends on the current state of the DFA, and that one can use a variety of DFAs with different set of states to represent a single regular language. The question here is whether the expected number of steps to record a desired story under an optimal policy depends on a specific DFA or it depends only on the language. We prove that the expected number of steps depends only on the given regular language and not on a specific DFA of that language. In fact, if two DFAs have the same language, then there is a bisimulation relation between their states, and each tuple related by that relation have the same expected number of steps to record a desired story from that state. In this paper, we study several language mutators which afford a great deal of flexibility in treating specifications and generally allowing us to broaden the treatment of stories. In this presentation, I shall mention only three mutators. Consider a scenario in which we want the robot to make within a single execution several videos for several recipients. As an example, consider a situation when each one of Alice, Bob, and Chris want the robot to capture a video for him or her. Those videos are specified by DFAs D1, D2, and D3. The robot captures a single event sequence and then post-processes that event sequence to subtract from it three subsequences, each one for one of those three recipients. This kind of scenario is implemented by two kinds of language mutators, a supersequence mutator and an intersection mutator. A supersequence mutator produces from a DFA-D a DFA-D prime whose language consists of all event sequences that are obtained by making supersequences of the sequences with the language of D. The intersection mutator produces a DFA whose language is the intersection of the languages of the two input DFAs. The final DFA is obtained by applying those two kinds of mutators on the input DFAs. Other scenario is for when the robot cannot record a desired story. In this example, the robot reaches a state from which can never complete a desired story. For that purpose, we alter the specification. In this example, we add a transition labeled D from state Q1 to state Q2. This scenario is implemented by a Levenshtein mutator who alters the specification to generate sequences that are within a Levenshtein distance of sequences in the original specification. An algorithm for this mutator copies the original DFA in 2K levels and adds appropriate transitions that account for insert, delete, and substitute operations. In our work, we considered 2 case studies, which we implemented using Python. For RTM with fully observable model, we solve the goal MDP using the value iteration method. For RTM and RTM with fully hidden model, we use the APPL online toolkit, which implements the dispatch algorithm. William is a tourist visiting Oulu in Finland. The districts of Oulu and their connections are shown in Figure A. William's family has secretly contracted a robotic videography company to record him visiting Kaupahalli, the Hypusaaret Park, and either Oulu Cathedral or Tuutima Museum. The robot doesn't know William's specific plan to visit those districts, but it does know through some statistics that a typical tourist move among those districts according to the event model in Figure B. The desired video is specified using the DFA in Figure C. The robot cannot spend all its time on following William because it is assigned other tasks as well. Thus, it must form a strategy that predicts which event to try to capture. For RTM with fully observable model, we compute an optimal policy for the goal MDP. The expected number of steps to record a story by that policy gives a theoretical prediction of the number of steps to record a desired story. We simulated the execution of this policy 1,000 times. In each simulation, William followed a random path through the city according to the event model, and the robot uses the computed policy to record a desired story. The average number of steps to record a desired story for those 1,000 simulations was very close to the expected number of steps. The average number of steps for RTM with a single useful observation and for RTM with fully hidden model were respectively 37.15 and 45.32. The single useful observation was a message the robot received from a security guard saying William is in District S1 whenever he was there. Consider that although in RTM there was only a single useful observation, the average number of steps is still fairly close to the average number of steps for RTM with full observability. In these figures, we have shown the distributions of the number of steps for those three problems. We have also shown for each experiment a pie chart that shows the distribution of the recorded sequences. For the second case study, we consider a wedding reception whose guests include Alice, Bob, and Chris. In each time step, which is about 10 minutes, each guest could be in one of the states of dancing, being entertained, drinking coffee, smoking, or drinking other beverages. Each of those guests asks the robot to capture a video for him or her. Alice wants to see Chris drinking coffee or smoking, and to share her last dance with Bob. Bob, interested in only seeing his own dancing, but also wants to share the last dance with Alice. Chris' family would like to know if Chris is drinking too much coffee or smoking too much. Each of those stories are specified by a DFA, and the final specification DFA is made by using the supersequence and intersection mutators. So the robot must record a sequence that has a subsequence within the language of each of those three DFAs. In this experiment, again, the average number of steps for RTM with fully observable model was very close to the expected number of steps. And again, as the robot's observability was decreased, the expected number of steps was increased. The only useful observation for RTM was an observation that allows the robot to detect if someone was smoking using a smoking detector sensor. One of the disadvantages of the approach is that it does not have low-level planning and motion planning. Also, creating a useful event model might be difficult for real-world applications. Also, it ignores uncertainties in sensing. In conclusion, as the robot's ability to perceive the world increases, the expected number of steps to record a desired story decreases. Also, sometimes even a stream of quite limited information can be very useful to reduce the expected number of steps to record a desired story. Future work can consider multi-robot extension, more realistic models, low-level planning and motion planning, and using machine learning techniques to different aspects of the problem. This work was supported by the National Science Foundation. Thanks.